All right, so today we have Luigi Tizzano give us some comments on continuous generalized global symmetries. Take it away.
Thank you so much, Julius, and for inviting me to this nice event. And it's a pleasure for me today to tell you exactly about some comments on generalized global symmetries that are continuous. And this is based on a work that we put out in June this year with another postdoc here at ULB, Jeremias Aguilera Damia, and also Ricardo Argurio that spoke at this event last week. And then I hope to have some time to tell you about some other directions that we are exploring with the same people, and also Daniel Brennan from UCSD. Okay, so I'll jump, So I'll start by telling you some general comments on global symmetries in quantum field theory, and in particular abelian global symmetries. And more particularly, I want to tell you something very basic about the Hooft anomalies. So for this part of the talk, I will be interested in a quantum field theory in 4 dimensions that has these 2 symmetries, these 2 ordinary U1 symmetries that I call A and C. And as we all know, we can often couple these symmetries to a quantum field theory by activating the corresponding classical background sources that I'll denote A1 and C1. So for the rest of my talk, whenever you see a parenthesis with a number, that means that the corresponding form as the dimension of the number that you see inside the parenthesis. And this will be all the case for the entire duration of the talk. And so, okay, as I was saying, we can turn on these background gauge fields and then couple the theory to the conserved current. And so I will denote the conserved current for U1A JA, and the same thing for the conserved current of U1C that I denote JC. And then, as we know, we can investigate if the theory is gauge invariant under background gauge transformation. And it is often possible that we can make the theory gauge invariant by possibly introducing additional local counter terms to maintain the invariance of the theory under transformation of A and C. However, there are cases in which this thing is not possible. And in those cases, I will be saying that we have a Hooft anomaly that is encoded by the following functional. One is called I6. I6 is commonly referred to as the anomaly polynomial. It is a 6 form in this case. And then it can be written as the total derivative of a 5-form functional that in this case takes the form of a Chern-Simons term in 5 dimensions. And both these 2 functional, I5 and I6, by the descent procedure, are related to the anomaly functional A, which is expressed in this way. And the anomaly functional A, in addition to being dependent on the background fields A and C, also depends possibly on their gauge variation. So let me be, yes.
What do you call it, Hooft anomaly?
What or why? Sorry.
Huh?
You're asking me what do I call a Hooft anomaly?
What do you call it, Hooft anomaly?
What?
I know anomaly matching, but what do you call it, Hooft anomaly?
Yeah, I'm just trying to, I understand there are different people use different terminology for this thing. I'm trying to differentiate the concept. So what I'm referring to as a Hooft anomaly is, as I said, something that violates the invariance of the partition function under background gauge transformation. So whatever functional you can measure under this transformation must be a functional only of background gauge fields. This is in contrast to more ordinary example of anomalies where we can also have operatorial violation of the background gauge of the global symmetry variation. And so I want to distinguish these 2 things, but I'll be even more specific in a bit. So if you wait a second, you'll see.
Okay, so you say it's not Adler-Bell-Jakim.
Yes, exactly. I'm going to be extremely specific if you give me 1 second.
Okay.
Okay, so now the anomaly polynomial, of course, as we all know, again, I'm only talking right now only about background symmetries, is this 6-form I6, and this is the most general way that we can write. It comprises the famous triangle diagram. We have the A cube anomaly, the C cube anomaly, and then we have 2 mixed anomaly that involve the A and the C anomaly. And crucially, as we all know, these anomaly coefficients are all integers. And this is a very important fact. And this also, it's very important because it explains that anomalies are extremely important because they are rigid under RG flow. And this indeed was discovered already a long time ago by Adler and Bardeen that showed that anomalies are one loop exact. And so in more modern way, one could understand this argument by saying that the coefficients being integer obey Norrie normalization theorems. But okay, so this has been known for a long time. Now, to understand better what I'm gonna do next, the next step is that I want to gauge the symmetry U1C, okay? And so in order to be able to gauge this symmetry U1C, I have to make sure that the anomaly functional that will be present in the current for the symmetry C is actually set to 0 in order for me to have a conserved current. And to do that, I'm going to make a choice of counter term in such a way that the anomaly functional that this polynomial produce, it's only presented in the current A. So I will only have a violation of the current A by the following local quantity. And in particular, it's very important, of course, if I want to be able to gauge the symmetry C, I must be sure that the cubic anomaly for this symmetry is 0. So of course, if the cubic anomaly is 0 and I make some counter term adjustment, I will, in the most general way, I will be able to present the anomaly for A in this form. Okay, so there are 3 pieces now. One that is the cubic anomaly for A, and then there are these 2 pieces that I have to study under gauging of the symmetry C. Perfect. So let me first begin by the situation where we have a theory in which the mixed anomaly that has 2 legs with C and 1 with A is 0. And so if we go back 1 slide, this is the situation where we have only this anomaly here and the cubic anomaly. And then we ask the question, what happens if we replace the dynamical gauge field C by, the background gauge field C by a dynamical gauge field, the little c. And so that in this talk, I will always denote dynamical fields by the small letter. So what happens here is very interesting because what we find is that inside the non-conservation equation of the current A, we find an expression that depends both on a background field F, but also on an operator FC. So according to what I just said, this cannot be a 't Hooft anomaly because, as I said, I define 't Hooft anomaly as being something that violates a current only by C number. And this one is clearly not a C number because it contains an operator in the right-hand side. However, when we set to 0 the background field A, so the background field for the other symmetry, not the symmetry C, but the symmetry A, we will find that this current is conserved and at separated points, and the symmetry U1A is not violated. So in order for us to understand what to do in this case, we must be able to address this non-conservation here in terms of data that are already in the theory when we gauge the symmetry C. And in order to do that, we have to study better what happens to this theory when we gauge the symmetry C. Okay, so the idea is that this anomaly functional written like this, it's problematic and we want to get rid of it. Okay, but the key point is that when we gauge a symmetry U1 in 4 dimensions, we should always remember that there's always an emergent global symmetry that we have to take into account. This is a magnetic symmetry. It is a magnetic one-form symmetry, which has a current with 2 legs. and it is related to the star of the dynamical field strength for the U1 field. And of course, we can, exactly as we do in the theory of ordinary symmetry, we can couple this theory to a background field, which we're going to take as B2. So B2 will be a two-form U1 background gauge field. And then we will study the coupling of this current JB to the theory by introducing the standard minimal coupling with B2, which I can rewrite as B2 wedge FC2. And so now, if I consider in my original theory the presence of this new background B, I can basically cancel this operator valued thing that I found in the anomaly functional A by postulating a new transformation law for B2. Remember that B2 is a two-form, and so I can try to adapt the transformation law of B2 to cancel the two forms that appear in the anomaly functional. And how do I do that? I modify the gauge transformation of B2 apart for a piece that is the D of a one form by a piece that depends explicitly on the gauge parameter of the symmetry A and on the background field strength F. And as you see here, very importantly, there is also the appearance of the coefficient for the A squared C Hooft anomaly. And so you see, the important thing is that this new field B will shift also under this U1 background gauge transformation. And in this way, we restore completely gauge invariance in the theory with the gauge U1C connection. And this, of course, for the expert of string theory is very similar to the Green-Schwarz-Witten mechanism. And so in full generality, we will say that a theory that coupled to this background field A1 and B2 such that enjoys this following background gauge transformation. So A changes in the standard way, but B changes by these shifts that depend on the U and A symmetry. And a theory in which this gauge transformation maintain gauge invariance of the partition function, it will be said to have an abelian two-group global symmetry. And this is a concept that has appeared in the literature in this form around 2018 and by the paper of Cordova, Dumitrescu, and Intriligator. And of course, there was also some precursor study in this paper by Kapustin and Torngren. And more generally, you could imagine to repeat this procedure for a mixture of global symmetries P with different P degrees, which will have higher form gauge transformation that are mixed with each other. And in this case, we will be talking about the concept of higher group global symmetry. So there is not just a two group, but in principle, you can continue and go on in the number with higher and higher form background gauge fields. And since the discovery of this phenomenon in 2018, there has been a lot of interest in the literature. And I'm sure that many people in the audience have worked on this topic. So, and we know already about many generalizations that include, for example, non-abelian zero form global symmetry, or even more complicated example where either the zero or the one form symmetry are finite or discrete. And so, as you can see, there has been a lot of activity that is still ongoing on this topic. And so, okay, one could ask, why are we interested in the two groups? And maybe also, is there anything dynamical that could be said about the existence of two groups? Like, does a theory that have a two group global symmetry have to respect certain certain dynamical constraints? And one interesting hint comes also from the following argument. There is, when you have a two group with continuous symmetry G1. So, for example, the case that I just told you before, there are only two allowed patterns of spontaneous symmetry breaking. Indeed, in the case you have a two group with the G0 and G1, the only two allowed patterns are that either you break down G0 and preserve only G1, or you break completely the two group. So another way to say this is that spontaneous breaking pattern where you only break the zero form symmetry inside the two group are not allowed. And this is very interesting. And it was proven by current algebra techniques in this paper, still by Cordova, Dumitrescu, and Intraligator. And one could wonder, okay, but imagine that I try to violate this type of symmetry breaking pattern, and what could I say about a theory that violates its pattern? And there was a cute observation in this paper that appeared a few years after the original one. That is, for example, you could consider some simple model that of effective field theory with axioms, and then you could try to, force a symmetry breaking pattern where you violate these two that I wrote here. So you want to break the zero form symmetry after the one form symmetry. And so if you try to do that, you're going to find that there is no, your effective field theory will not be under any control. And so in particular, you're going to be able to prove an inequality between energy scales. And so you're going to prove that in these models, the scale at which axion can decay will always be larger than the scale at which other charge object get a mass. And so this is like a quite interesting phenomenon. And I just want to add a comment related to this phenomenon, that currently it is not completely clear if there are also constraints of this kind when you have a G1, so a one-form symmetry that is finite. And the reason why we don't know yet of this kind of constraint is that to prove the theorem that I just told you, we really need the existence of conserved currents. And so it will be very interesting to understand if we can repeat or find more general patterns in which two groups can be broken, even in the case where G1 is finite, and maybe try to understand what are the dynamical implications of this setup. And I'm saying this because some of the most interesting two groups that seem to be found are in the context of superconformal field theories, for example. And in those contexts, it is always the case that the group G1 is finite. So having some handle on what dynamical constraint exists for the two groups in this case would be very interesting. And yeah, I think this is an open question. And yeah, I just wanted to point it out. Okay, so this concludes for the moment the discussion of two groups in 4 dimensions. And now I want to try and replicate this discussion also in 3 dimensions. So, but as we saw in 4 dimensions, continuous two group can be introduced basically by gauging this symmetry U1C in a theory that has a mixed anomaly between a U1A and a U1C symmetry. But if we try to do this, if we would like to do this program in 3 dimensions, there are 2 immediate problems that you are probably all familiar with. The first one is that the continuous U1 symmetries in 3 dimensions do not admit anomalies of the kind that we already discussed before. So there are no perturbative Hooft anomalies for these U1 symmetries. And in particular, and moreover, if we try to gauge a U1C symmetry in 3 dimensions, we do not get a dual one-form magnetic symmetry in 3 dimensions. So it looks like the problem of defining a two group in D equal 3 is hopeless. However, to overcome both of these problems, there is a handle that it is inside the theory of anomalies. And to find this handle, we have actually to consider a generalization of the notion of anomalies. So we are all used to the idea that a theory of anomalies can be described in terms of local functional of background fields for the global symmetry that are under consideration. However, more recently, it has been proposed that one should extend the theory of anomalies to allow also for space-time dependent couplings that appears in the theory. And so if we have couplings that can be space-time dependent, there might be a sense in which we can extend the theory of anomaly to accommodate for such situation. And instead of trying to explain in formal ways what is an anomaly when you turn on these space-time dependent couplings, I will just tell you of a simple example in which this is an interesting thing to do. So consider a 2-dimensional pure gauge theory, okay? So this two-dimensional pure gauge theory will have the standard kinetic term dA1, but we couple this kinetic term covariantly to a two-form gauge field B2 that is associated to a U1 one-form symmetry with the two-form current dA. And in addition to this term, we want to consider a theta term. And again, we are shifting dA by B2 because we are trying to couple the theory to this electric one-form symmetry. However, if we inspect the partition function of this theory, so we study it as a function of theta and B2, the shift of theta by 2 pi will land us with a term that depends on B2. And so the ratio of the partition function after a transformation of theta with itself will give something that depends on some counter term that depends on B2. And so in a sense, we could say that there is an anomaly between the periodicity of theta and the presence of a background field for this U1 one-form symmetry. And the anomaly is detected by this phenomenon. However, we can actually understand this phenomenon completely in terms of the anomaly inflow that I told you at the beginning. And the way to do that is that we just have to think about theta as a background scalar field that takes value in a circle. And then, so if theta is a background field, we can extend both theta and B2 to a 3-manifold and talk about a 3-dimensional anomaly of the form theta times dB2. And by the descent mechanism, we know that this 3-dimensional anomaly will be associated to an anomaly inflow polynomial I4, where we have d theta dB. And so heuristically, we can think that this anomaly is, if you are not at ease with the idea that theta is some kind of field, you can actually heuristically think that theta will implement a symmetry. But in this case, the symmetry that it has to implement will be a -1 form symmetry. In this sense, a -1 form symmetry must only be coupled to something that has no legs. And so that's the reason why the background scalar, the background field will be a scalar. And so if we view theta as a background for a global symmetry, what will happen is that we have to think about theta as this particular type of gauge field whose transition function will jump by 2 pi times an integer. However, d theta is a perfectly well-defined thing across overlaps, and we can think about d theta as its field strength. And so then anything we know about the standard picture of anomaly inflow can be reproduced also in this case using d theta instead of ordinary gauge fields. And so now we can move and try to apply this technique to a model, a concrete model in 3 dimensions. So let's consider a 3D model that has a U1 global symmetry and a single boson field chi that transform non-linearly under this symmetry U1A. So with this transformation chi going to chi plus lambda. And then of course, as before, we want to turn on a topological coupling theta, which in this case, it's a topological coupling between the derivative of chi and a background field strength for the symmetry U1A. And the last term here, the B tilde 2 times dk, it's a coupling of the theory to another higher form symmetry. There is a U1 one form symmetry associated to a current that is star of d chi. And so this is the most general action coupled to all the background fields. And an interesting thing is that in 3 dimensions, you can prove a generalization of the Coleman-Mermin-Wagner theorem. And this will tell you that in 3 dimensions, a U1 one-form symmetry can never be spontaneously broken. So this is a cute fact that can be proven by generalizing the ordinary theorem. And in particular, these two symmetry, the U1 one-form symmetry B tilde and the U1A, yes?
This will be in any codimension 2 symmetry?
You mean in 3 dimensions?
Yeah, you said that there is a one form in 3 dimensions.
Yeah, so a one form in 3 dimensions, and then you continue. There is a yeah, you continue like, so in 4D, you can do it with two-form symmetry, cannot be broken in 4D. And this I'm talking about continuous. And then if you want to do discrete, you have to say, you know, it's 1 degree less, exactly like in the ordinary. So in 3D, you can break spontaneously a one-form symmetry that is discrete. But in 2D, you cannot do it, you know, because it's one with the discrete thing, it's 1 dimension less.
I see.
Okay.
So Coleman used the 2-point function of the scalar field.
Yes, exactly. This is very interesting. You can do something very similar to that. And there are 2 papers that do, sorry, I didn't put the citation. There's a paper by Hoffman and Iqbal and a paper by Ethan Lake. And they do a very similar computation a la Coleman. So now you will, you know, for example, if you want to do a one-form symmetry, you will source a line, and then you have to look at the propagator in presence of this line. It will have some unphysical logarithmic divergence, which now will be in some higher dimension because it's very similar conceptually, very interesting.
Okay.
Okay, so and another thing which might be unexpected by the practitioner is that in these simple models of Goldstone that have only a U1 symmetry, and now we know also this emergent U1 one-form symmetry, there is a mixed Hooft anomaly between U1A and the one-form symmetry U1B. And the mixed anomaly takes this form. And to prove that this is a mixed anomaly, and you just basically have to take this action and do the background gauge transformation.
Question.
Yes.
So you could dualize chi into a photon, and then the global symmetry would be the topological symmetry. Does this give any insight?
Yeah. Well,
or maybe does this theory appear?
I have to think about that. That's an interesting point, but I wouldn't know right now of any sorry, I don't have anything to say about this, but this is a point that should be, yeah, I should think a bit more about it. Maybe we can talk more about it later.
Thanks.
Okay. So now so exactly as in this story of the anomaly in the space of coupling, what I want to do is that I want to think about this theta that we introduced here as the background field. So I'll take it to be a background field that is circle valued, and of course then it will vary in space-time. But now the story will be much more subtle, because if theta is a background field, we are producing more anomalous term that contributes to the functional. And in particular, there will be something that looks like this term. So it will have a gauge variation for lambda, and then something that multiplies d theta, wedge the background field strength for A. And now the entire point is that we are in the perfect shape to replicate the story of the 2 groups, because all we have to do is to think about this background field that is a scalar, is a background scalar that is circle valued, and we want to promote it to a dynamical field. So it is a dynamical field that is circle valued, and these are a very well studied example of axioms. And so if we render this background field dynamical, we will run again in the same problem that affected the discussion of 2 groups in 4 dimension, because explicitly this anomaly functional here will have something that depends on the operator d phi. But again, similarly to the story that I told you in 4 dimension, in the moment that we gauge this symmetry associated to the theta parameter, we get actually 2 new global symmetry. We get a new shift symmetry that I called A tilde, that is an ordinary symmetry associated to the shift symmetry of phi. But more importantly, we get a new background field a new one-form symmetry that is U1, associated to the current star d phi. And now what we can do is couple this new theory where we gauge the parameter theta. So this will be a new theory with the dynamical phi and chi, coupled to all the background that you have at your disposal. So apart from the appropriately covariantized term, you will find these three couplings. So what was the topological coupling that now has these two pieces that are dynamical? And now we have this coupling to B2 and to B tilde 2 for the higher form symmetries. And so the idea now is that this action can be rendered completely gauge invariant if we adjust the transformation of B2 and B tilde 2. And by this analysis, we can again conclude that even in 3 dimensions, even though there are no ordinary Hooft anomalies for U1 symmetries, you can still produce an example of abelian two-group global symmetry that takes the following form. It involves 4 groups in this time and not only 2. And both the ordinary groups transform traditionally with the standard gauge transformation, while the B2 and the B2 tilde will have some transformation that are mixed with the transformation both of the gauge field A and A tilde. And an interesting thing about these models is that, they are extremely simple. And of course, they can be generalized in many directions. You can add more couplings or couplings to other fields. And so they can made much more rich than what I described for you today. And in particular, I believe they are an interesting starting point to understand various aspects of these generalized global symmetries in 3 dimensions. But one of these generalization actually shows some unusual features that I will now discuss for you. And so let me move to a model that is connected to this model.
Question?
Yes.
The transformation for B2 tilde, the third term, is it possible that there is a typo with the?
No, it's exactly like that. It has tilde and ordinary A. Yeah, it is like that. Because as you can see here, I can tell you the reason why in this expression there is no expression with F tilde A. So
okay.
You can do the exercise. It's extremely elementary. You just sit down and do all the variation. Okay. Sorry, I can't hear you.
Sorry, it was muted. Yes, thank you very much.
Okay. Okay, so let's move to a slightly more complicated model. Now so I'll start right away from the model where everything is dynamical just for simplicity, but as before, we could have started with a model where many symmetries are a background. And so I'll take 2 Goldstone this time. I'll call them chi and phi. But now I want to couple them to a dynamical U1 gauge field C1. And what we can do very quickly is we can compute the equations of motion for this theory. So we can compute the equation of motion for the current associated to the shift symmetry of chi, which is JA. And then we can compute the equation of motion for the current associated to the symmetry of phi, that is A tilde. And then this theory will have also an electric one-form symmetry that is modified by the presence of this matter chi and phi in this way. So JE2 is a current for the electric one-form symmetry. And so by the equation of motion, you can convince yourself that for any integer value of k greater than 1, the U1A and A tilde symmetry, shift symmetries, and the electric one-form symmetry U1E are explicitly broken to discrete subgroups. Because if you try to exponentiate the star of this current, you will only find the topological operator by some phases that take finite values. And again, this is a more rich structure and it's a more richer situation where even though some of the symmetry have become discrete, we can still show that this 3D model has a 2-group global symmetry. And so the groups that are involved are many. So we have the discrete shift symmetries, the discrete electric one-form symmetry, and then we also have a magnetic zero-form symmetry that is precisely similar to what Stefano was talking about before. And then we also have 2 one-form symmetry associated to the star of d chi and d phi. And to obtain the background gauge transformation, there's just a technicality that one has to remember that, you know, if you want to write background gauge transformation for this zk valued field, what you have to do mathematically is you need to introduce a cocycle that's a p+1 cocycle that is zk valued. And then it's convenient to do that by also considering a flat U1 gauge field AP1, such that the gauge equivalences of these flat gauge fields are set to be equal to 2 pi over k times the cocycle. And so then you can write down a very involved set of background gauge transformation. I just wrote down one here for the field B, but you can do it for all the other fields. And wherever you see things like lambda A or or other things that depends on these symmetries, you have to remember that we are using this identification with the cocycle. And so even in this case, that is more, let's say, exotic, we can still find all this general structure. But of course, all this discussion, as you could see from the previous set of equations, relied on the choice that we made, so that the integers were all k, the integer k was greater than 1. And so automatically you will be led to think that when you set k equal to 1, there's nothing much to be said about this theory. And this is probably where the most interesting part comes in. Okay, so let me try to explain why we would be saying that for k equal to 1, there is nothing. Because of course, if we take k equal to 1, we see automatically that the symmetries, the shift symmetry for chi and phi and the electric one-form symmetry will be completely broken because of their non-conservation equation. And so there is no phase, there is no value of the phases that we can tune to preserve any discrete subgroup. But probably this is a too quick observation. And what we should be doing is that instead, that we should be looking at the topological operators that are associated to this symmetry. So what we should be doing is to look for operators U alpha and U beta, which are obtained by taking the integrals of the star of their related currents. And as we can see, as I mentioned before, the problem with this operator U alpha and U beta, it's clearly that they won't be topological, because whenever we try to deform sigma 2, we will pick out a piece that depends on d of star j. And because of this non-conservation equation, there is nothing that we can do to save their topological nature. However, it turns out that this is also too quick, because there is something that we can do that is a bit more clever. So the idea is as follows, and I'm gonna do this for the current, for one of the shift symmetry current, but you could have done the same also for the higher form symmetry current. So you define a new current that you call J hat, and this new current will be the ordinary current, and plus the piece that was spoiling the conservation of the unhatted current. In such a way, we formally obtain an equation that is manifestly conserved because we just canceled the piece that was problematic. And then if we were to use as a new definition of topological operator, an operator that depends on the current hatted, we will see automatically that this is a topological operator. And this would be an improvement. However, if alpha is a generic angle between 0 and 2 pi, the operator U alpha will be still, as I said, a topological operator, but not gauge invariant. And gauge invariance will be spoiled because of the coefficient of this term in front here. And of course, a similar manipulation, as I said, could be performed for the topological operator of the one-form symmetry current. But so there is something more special to be said, though, in this case, that if we set these values of the angle alpha, so we set alpha to be equal to 2 pi over n, then we can go back and analyze, sorry, let me go back. So we can go back, plug inside here 2 pi over n, and analyze the role of this piece here, so the non-gauge invariant piece. So the non-gauge invariant term will be the following action. It's I over 2 pi times n phi fc. But this action here, the phi fc theory, is a very famous action. So because it is a BF theory in 2 dimensions. The only problem of this action is that it is improperly quantized because of this n at the denominator. So this n at the denominator renders this action non-gauge invariant. But this problem is just, in a sense, a superficial problem, because we do know of a way to render this action gauge invariant by introducing extra auxiliary dynamical fields that I call rho and B1. So I'm going to introduce 2 new fields, rho and B1. Rho is a scalar and B1 is a gauge field, and these fields will be confined to live on sigma 2. And I'm going to show you that when you introduce this field rho and B1, we can write a new expression that is completely gauge invariant. And in fact, the end shot of this analysis is that whenever alpha is 2 pi over n, we can define a gauge invariant n topological operator by combining the current with this piece over here. Okay, so this piece over here is a way to write in a fully gauge invariant way the term that I wrote at the beginning. And the way to see that is to solve the equation of motion a bit heuristically for the field rho and B. And as I said, the dynamical fields rho and B1 only live on this surface sigma 2 and not in the full space-time M3. And so the upshot is that by doing this dressing, so we took a current and we attached this piece here, that is a 2D BF theory coupled to certain fields rho and phi, sorry, rho and B1. We obtain a new topological operator that is labeled by these angles 2 pi over n. And this has a very unique and particular structure now because of the following reason. So the price that we have to pay to introduce this operator D is that what we called a U1 symmetry before will no longer be an invertible symmetry. What do I mean by that? I mean that if I consider an operator D for this that I just defined, that I defined for this symmetry U1A, and I consider the dagger operator for this symmetry, so the Bard operator for this symmetry, I can take their product and I can manifestly show that the product of D and of its dagger will not give you something that is 1, but will give you another non-trivial defect operator that is called C. So this is a combination of the, well, you just have to take the product of these 2 defects and you're going to find generically that this is a non-zero and non-trivial operator that is called C. And this is an operator that is confined on sigma 2. And so the upshot of all this analysis is that even though this U1A symmetry is broken, it is manifestly broken by, if you want, the equation of motion of the currents that we introduce. We can still talk and describe a set, an infinite set of non-invertible topological operators that are labeled by this angle 2 pi over n. And it's quite surprising that you can find such a restructure in such a simple model. I find it striking. And all these ideas are rooted in something that has been developing very recently in a lot of direction, which is the idea that whenever you, until maybe a couple of years ago, we would have said that whenever we find a global symmetry, it is very simple to associate to this global symmetry a topological operators. However, it has been more and more clear that there are topological operators that are not necessarily associated to the notion of ordinary or generalized global symmetry. But it has been emphasized by various people over the year that we should also enlarge our notion of symmetry to include the action of these non-invertible operators. And in particular, in the context of 2D CFT, this was known for a very long time, since the work of Verlinde, or in more recent times, since the work of this gentleman on the Ising CFT. And since this idea have picked up in more recent years, there has been a flurry of activity in trying to define symmetries like the one I told you, or completely discrete ones that don't start from the group U1. And as you can see, there are a lot of papers, and I'm afraid I might have missed someone, but it's an extremely active area and there are results every day. And I just want to emphasize, though, that among the paper that I cited here before, our work is particularly influenced by a similar analysis that has been done in 4-dimension a month before we put out our paper by this group of authors. And this is precisely also related to the discussion that we had at the beginning with Ami about the ABJ anomaly. So let me just make a parallel with what I just told you in 3-dimension. So imagine that we take the QCD Lagrangian and we only consider the massless up and down quarks. And then we set ourselves below the electroweak scale, where this SU2 times U1 is xed only to U1. And so we basically can describe a theory that is QED below the electroweak scale. And so, of course, we know that this theory will have an axial current, JA, which suffer from an ABJ anomaly. And again, I want to emphasize that the ABJ anomaly is of a different taste with respect to what I told you at the beginning, because as you can see, in the right-hand side of the non-conservation equation for J, you have an operator that is the dynamical field strength F wedge F. And of course, we know that from the anomaly argument that the axial symmetry is broken quantum mechanically to Z2. But what was discovered by these authors that is more surprising is that if you set a general set of rational angle equal to pi over n, you can again find infinitely many non-invertible operators, again starting from the anomalous U1A symmetry. In this case, instead of an improperly quantized BF theory, what you find is an improperly quantized Chern-Simons term that can be fixed by decorating the defect D with a fractional quantum Hall state, which is a Chern-Simons coupled to some other auxiliary field in such a way that you can fix the non-gauge invariant. So the construction is philosophically extremely similar. But this last point then raises a further puzzle that one could ask. So at the beginning, we talked about the general structure of theories and their anomalies. And so then we could go back and try again to look at anomalies in 4-dimension and consider a QFT in 4-dimension that has two symmetries, U1A and U1C, and an anomalous U1A current where we pick this theory in such a way that there is no cubic anomaly for now for simplicity. So this theory right now will have two global symmetry anomalies, one for A squared C and one for AC squared. And so the piece on the right here, the one with FC, upon gauging the group U1C so upon gauging U1C, this piece on the right will produce an ABJ-like anomaly and will produce for us an infinite set of non-invertible symmetry defects. So when we set this piece to 0, this will be the construction that I just outlined for you in QED. But when we set the ABJ anomaly to 0, we can talk about the two-group global symmetry exactly as I did at the beginning of the talk. So the natural question to ask then is, what happens when you want to keep both Ka squared C and KAC squared different from 0, and at the same time gauge the symmetry U1C? So this would be a more general situation where both these anomalies are turned on. And you might imagine that this is like a very exotic situation and you cannot find many theories that do that, but actually it's actually a very generic situation. And so there's a funny theory that we've been playing around. So there's a theory that I call the 3, 4, 5, 6 theory. So you take two Dirac fermions and you decompose them in 4 Weil fermions with the charges below. So under U1A, they have charges 3, 4, 5, and -6. And under U1C, they have opposite charge 1, -1, 1, -1. So this theory do not have any cubic anomaly. You can prove it yourself that both cubic anomalies are 0, while it has a non-zero A squared C and AC squared anomaly. And so what you have to do, again, is try to gauge the symmetry U1C. And you will find an even more general symmetry structure that is characterized by new type of symmetry defects D that are confined to live on a 3-manifold. And this, in a sense, generalizes what I told you about the QED story and also the Goldstone-Maxwell model. So one has to define these more general symmetry defects that would make sense in this kind of situation. And what's interesting is that when we do this gauging now in 4 dimension, as I told you before, there's also a magnetic symmetry, U1M, whose current is associated to the star of the dynamical U1 gauge field, because this is just like QED with 4 Weyl fermions when we gauge the symmetry C. But however, there are also corresponding ordinary symmetry defects for this magnetic symmetry. And so one has to understand this more general symmetry structure where you have these non-invertible defects D tilde, and also these defects U, which a priori lives in objects of different codimension. But in this more general symmetry structure, you have to start considering the non-trivial fusions between these defects D tilde and the defects U. And I just want to emphasize that very recently there has been a lot of work in trying to formalize the notion of categorical symmetries in quantum field theory. And it is probably true that this is also the language that I should be using, just I'm not so well posed in this technology. And so right now, I cannot tell you right away if this is exactly what we are finding. But I just want to point out that there are some interesting recent papers where these ideas are being developed from a more mathematical perspective. But the interesting thing about this model is that it's extremely simple. And once you find this new symmetry structure, you can ask also other type of question related to, for example, where does this theory flows to, and how do I match this symmetry along various RG flow? For example, you could add a complex scalar to this QED theory with some charges QA and QC. And then, for example, add a mass term to the complex scalar and, for example, flow to the free theory, and then try to match the non-invertible structure there, or add an Higgs potential and completely remove Higgs down the gauge field, either to nothing or to some discrete TQFT, and then describe this new symmetry structure there. Or study, of course, Yukawa interaction that can give mass to the fermions. And so these are extremely rich theory that we are studying and generalizing, and we believe that there are many more examples that also exist in 3 dimensions that we can describe in the near future. Okay. And so with this, I'm getting to the conclusion of my talk. And so the upshot is that even though U1 global symmetries seem to be something extremely simple and something that we always thought we understood very well, I just wanted to point out that there are various generalizations of this notion that, of course, involve the more familiar higher form symmetries, the more recent development of higher group symmetries, and the even more recent non-invertible symmetries. But these can all be obtained by these U1 global symmetries, which have a lot of physical application. And so this is a very exciting perspective, in my opinion. And because all this structure gives us more data about quantum field theories, the most exciting possibility is that there will be new and more refined non-perturbative results that we can extract out of this tool. And of course, right now, we are still at the infancy of this program, and I think we should push more in this direction. And indeed, this is one of the short-term goals of myself and my collaborator, to try to understand all the dynamical consequences that are implied by these symmetries. And with this, I thank you very much for your attention.
All right, let's thank Luigi. And of course, questions are welcome. So, okay, as a non-expert in this, I'll just ask, after you talked about 3D and 4D,
yes,
did you think about, for example, 5D?
Yes, I do.
The cool stuff going on?
Yes, there is. This is also something that I'm doing with, I don't know if he's in the audience, with Pietro Benetti Genolini. Yes, yeah. So you can also try to do things in 5 dimensions. And we believe that we have a construction for this, and we hope to report also about that at some point. And then, of course, I should also mention that if you are interested in abelian gauge theories in 5 dimensions, there is a construction already in the market by Ricardo, Eremias, and Eduardo. But those are only abelian gauge theories. So, but I do believe you can be more general and describe this in also general 5D gauge theories.
Very good. You have more questions? Okay, then let's thank Luigi again.
Thank you.
So, very nice. And